Okay, so how is everyone today? Okay, so we've been talking about sequences and series. So the place that we are. Oh, by the way, I forgot to mention is that we count in base 10, right? Count in base 10. Why do we count in base 10? Is 10 like special or something? Like the number pi is special. It actually is special. Because no matter where in the universe you draw a circle, and no matter how big or how small, if you measure the ratio of the circumference to the diameter, pi is going to show up. But what about 10? Is 10 special in that same kind of way? Also, here's the deal: is that every culture that has ever been considered, written down, that exists now, or we have any record, they all count in either base 10 or base 20. And in some cases, they count in at least one base. They count in base 10 and also in base 60. So the 60 has a good reason, but why do you think 10 and 20? I'll give you a hint.
We have that many fingers?
We have that many fingers. That's it. That's why we count in base 10. And if we had, it's just a pure accident that we have 5 fingers on a hand. That's just a complete historical accident. The symmetry, bilateral symmetry, is sort of obvious, right? So surely we're going to have an even number of fingers because we're going to be bilaterally symmetric. But there's no really good reason to have 5 on a hand rather than 4. So I guarantee if you could wind the clock backwards and rearrange things just a little bit, and if we had 4 fingers on a hand, I guarantee we wouldn't count in base 8. I mean, in base 10, we would count in base 8. Yes?
The 61? What did you say that was important?
60?
Yeah.
So 60, in the end, is important for 2 reasons. So by the way, why is 20 important? Fingers and toes. And 60 is important independent of those things. The reason why is that 60 is a highly composite number, which means that you can make fractions of 60 lots and lots of ways. So like half of 60, 30. A third of 60, 20. A fourth of a 60, 15. Right? So it breaks evenly into many different things. And in the end, sort of the most abstract mathematical reason is that it turns out that there's something called abstract algebra and group theory, and 60 is a special number where a group is the smallest group where something ceases to be something called solvable. So that's basically the reason why 60 is important. But 10 is important only to human beings because we have 10 fingers. But if we meet aliens with 8 fingers, I guarantee they're going to count in base 8. Computers count in base 2. They count in base 2 because they've got little devices in them called transistors, and the transistors exist either in a low voltage state or a high voltage state, so there's just 2 states, and those represent, that's how it ends up counting in base 2. So, when we write 25 on the page like that, of course that means 25 in base 10. Right. So then if you ever take a computer science class or more abstract math classes where you're switching the base around, you would end up writing it like this, 25 and then subscript 10, which is to say that we're talking about 25 being reckoned in base 10. But what would 25 be if you reckoned it in base 8? So in the end, the reason why it says 2, 5 is because there's 2 10s and 5 1s. That's what 25 means. So how many 8s can we get in there? We can get 3 8s because, if I ignore the base 10 issue, do you observe that we can get an 8, an 8, and an 8? We can get 3 8s. And then after you've taken away those 3 8s, can you take another 8? No. So then there's just 1 more. So as a result of that, 25 in base 10, how do you write it in octal? 31 in base 8. Now, this is called decimal because deci means 10. And base 8 is called octal, you know. And so some other situations, you might not write 25 subscript 10. You might write dec, as in decimal. So decimal 25 is the same as octal 31. And that's the reason why mathematicians and computer scientists can't tell the difference between Halloween and Christmas. Right? Because decimal 25 is octal 31. Okay, good. Now that we have the important stuff out of the way, we've been talking about sequences. Remember that a sequence is a function from naturals to reals. You plug in a natural, and out comes a real. And understand that that means that some of the time the sequence can be defined starting at 0, so like defined at 0, 1, 2, etc. Sometimes it's defined starting at 1, but it can be anywhere, but just generally naturals to reals. And then you can think of a sequence as sort of like an infinite list of numbers. It's infinitely many. Then what is a series? Yeah. So it's sort of like saying, well, suppose we have this list of infinitely many numbers. And, the series is, can you add them all up? So some cases are trivial. So like if you have infinitely many zeros, so like the first one is 0, the second one is 0, the third one is 0, or, infinitely many zeros, then you can add them all up. But if they're all something else, like if they're all ones, can you add them all up? No, because that's infinitely many ones. That doesn't converge. All right. So now, given I could say let AN be a sequence. Be a sequence. The sequence of partial sums is what we talked about last time. So the sequence of partial sums is a sequence. So S0 is A0, which is to say that the first term in this new sequence that I'm defining is the first term in that sequence. And then S1 will be A0 plus A1. And then S2 will be A0 plus A1 plus A2, right, all the way down the line, generally speaking. So then, as we mentioned last time, that means that SK, you could write it like this. You could say, well, that's the previous one, so the one that came before it, and then what? You add AK, which is to say, look, S2, for example, is S1 plus A2. Okay? So then what we say is we say, therefore we can say that that this, the sum from I is 0, to infinity of AN, AI. My brain is like having a hiccup there. So if we want to compute the series, so what we can say is that that actually we can view it like this. This is the limit as k goes to infinity of the sum from I is 0 to k of AI, which is to say that this is saying try to add them all up. That's what that's saying. And then inside of the parentheses there, is that saying try to add them all up? No, it's saying try to add them all the way up to k. So like maybe the first 10 of them, or maybe the first 10 million. So that is exactly this. So inside of those round parentheses, I can write something much simpler. What can I write there? I can write SK. That's what it is. So what we're saying is that really what a series is is that you take a sequence and then you construct a new sequence, the sequence of partial sums, and then whether or not the series converges is identical is an identical question about whether or not that sequence of partial sums converges in the sequence sense. Okay, so now let's have a sequence that's not sort of trivial, like it's not all zeros and it's not all ones, and let's ask, does it converge? All right. So this is like the first sort of meaty one that we've done. All right, so then I can say let an be 1 over n. So again, that sequence is so important and famous that it has a name. What's its name? The harmonic sequence. And then we could ask, does the summation from I is, where do I need to start? Can I start at 0? No, I can't start at 0, right? Because you can't divide by 0, so I'll start at 1. So does the summation from I is 1 to n of 1 over n? So that series is so important that it has a name. What's its name? The harmonic series. So what we're asking about the infinite summation that is 1 plus a half plus a third plus a fourth plus ... So we're asking, does that converge? So now, what we're adding is getting small, right? So, we have this much, and then we add a fourth, so that's a little bit. And then we somewhere we're going to get over to like 1 over a million, so we're going to be adding 1 millionth, right? So that's small. So you're kind of asking, is it going to plateau? Is it going to sort of like inch up to something? Or is it going to, or are these big enough to where they're going to keep going forever? Which one? So, maybe it's conceivable, it seems to me, if I could delete all of the information that I know about it, it seems conceivable that it could plateau. It seems conceivable that it could go on, it could get arbitrarily big. So here's the idea, is that as it turns out, let's collect as many ones as possible. All right, so let me explain what I could possibly mean by that. So the terms of the sequence, the first one is 1, right? First one is 1. So then, so what I want you to see is that if we're taking terms of the sequence, I can get 1 by just taking the first term, right? So I can say 1. Okay, so I got a 1. So now what's the next term in the sequence? It'd be half, right? So half, and then is that enough to be 1? It's not, right? So then fine, plus a third, is that enough to be 1? No, because that'd be like, this would be 3/6, and that'd be 2/6, so that'd be 5/6, so that's not enough. And then what about this much? Now do we have 1? We got a 1. So we know that the sum is at least 2, right? Because here that's 1, and that's at least, that's a little bit more than 1, so the sum's got to be at least 2. But suppose that I take like 1 more. What if I take 1 more and say like a fifth? Something like that. Is that what I want to do? Let me think about this for just a second. want to make an argument. How can we do it? So how can we argue that this is definitely going to be, we could calculate it, but how can we argue that it's definitely at least 1? Because I want to do it again a little later. I want to keep going and collect as many 1s as I possibly can. What do you think? Let's write some more terms in the sequence. How about a fifth? So is that if I just stop there for a moment and write the next one, a fifth, that's less than 1. So then now I'll take a sixth. Is that 1? No. So a seventh and an eighth. So I'm going to need a calculator here because I can't really do that in my head. So a fifth plus a sixth plus a seventh plus an eighth. So that's 0.63, so I need to keep going. So, if they're getting small too quick, then I won't be able to do it, right? I wouldn't be able to do it. So then plus a ninth plus a tenth. So now I'm at 8/4 plus 1 over 11 plus 1 over 12 plus 1 over 13. Oh, look. I had to go out to 13, but I made it. So I was able to get another 1. So we know that the sum is at least 3. Right? So that's this is more than 1. This is more than 1. And so now the question is can I keep doing this forever? Can I take a 14th and then go out pretty far? So why am I going to be able to do this forever for this particular sequence?
Smaller further down?
Mm-hmm. But why can I always select enough of them? It's not that there's infinite amount, because remember the beer pitcher game, right? We kept adding half of what was left. Did that end up getting infinitely much beer? No, right? That was a finite amount. So what I'm saying is that if the mathematicians lined up and said I'll take 1 pitcher, and the next one said half, and the next one said I'll take a third, and the next one said I'll take a fourth, this is going to end up being infinitely much. But why? Why? Sorry?
Because we didn't have the finite limit that it would reach to.
It's not that.
Because you're almost taking up a portion of what's there.
Okay. So let me ask this. Let me ask it this way. All right. This is a 13th, right? How many 1/13ths would I need to take in order to get 1? I'd need 13 of them, right? I need 13 of them. So like if how many things are here? There's 8 of them? So no, 9 of them. Because there's a 5th, a 6th, a 7th, an 8th, and then I elided some, and then there's a 13th. So there's 9 of them. So if I switched all of these to, if I switched that to a 13th and all of them, that'd be 9/13ths, right? That'd be 9/13ths. So this is not ringing any bells? We're not seeing anything here? No, I'm getting some head shakes. Let's think about it. What if we consider the sequence of partial sums? So if we consider, say, SK. SK is 1 plus a half plus a third plus ... plus 1 over K. All right. So so here's an interesting observation. So this is how many terms are here? There's K terms. There's K terms in that sum, and this is 1 over K. If we were to and all of them, every term is greater than or equal to 1 over K, right? if we were to switch them all, to 1 over k, then what would the sum be exactly? It'd be there'd be k 1 over k's. So the sum would be 1. Okay, so this is what I want you to do for homework. This is a good exercise. So consider why. Why can we always get another 1? So why can we do that? And that's in contrast to the beer game. We can't do it with the beer game. We won't be able to get a full pitcher once we get the first full pitcher. Why can we always get another 1? So you do this for ungraded homework. And doing that, we can say, the harmonic series diverges. It diverges because you can always take enough terms to get another 1. So you can say, well, it's got to be at least 1. Then you can take enough to get another one and say it's got to be at least 2. And then you can take another one and say it's got to be at least 3. And then you can take a lot of terms, but finitely many, and you can say that's 1. So it's got to be at least 4. So it is going to get arbitrarily big. All right. So here's another one. Let's consider the beer game, but completely abstractly. So a sequence is called geometric if A0 is some fixed constant A. A0 is some fixed constant A, and AK is the previous one, AK minus 1, and then you multiply by R. So we need A to be positive, and we need R to be non-zero. So a sequence is called geometric if that, yes?
Just out of curiosity on the last thing.
Yeah?
With what you said, is it because it's infinite? Because whatever the smallest number it takes to get 1,
Mhm.
you just need that many terms in front of it, and because we have infinite,
Yeah, but you already took some of them.
yeah, but you just move further down until there's that many in front of it, and then it's 1, right?
That's the way you need to argue.
Okay.
Okay, so then, so for this, an example of this would be something like maybe A0 is 24. Oops, 24. And we could say that AK is AK minus 1 multiplied by 14. So let's write out the first several terms in the sequence. Okay, so then A0 would be 24, and then here's the idea is that the way that you get the next term in the sequence is you just take the previous one and multiply by R. So I'm not going to bother multiplying it out, rather I'm going to write 24 multiplied by 14. So that would be the next term in the sequence. How do we get the next one, A2?
24 times 14 times.
Right. So I'll say it like this, 24 multiplied by 14 squared. Right. So then how do we get A3?
42 times 14.
Right, 24 times 14 cubed, right? And I think that we can continue this and say, you know, ... What would be the formula for AK?
4 times 14.
Right, it would be 24 multiplied by 14 to k. Because you've got some first term in the sequence, and it's whatever number that you like, 24. And then the way that you get to the next one, the way that you shift to the right, you multiply by r. And the letter R is chosen because it's a ratio. Okay? So then the beer game is a geometric sequence because the first person is saying, I'll take 1 pitcher of beer. And the next request is always half of the previous size. So that person says, I'll have half of what he had. Right? So as a result of this, we can say that every geometric sequence is representable in the following way. We can say that the formula for AK is A, the first term in the sequence, multiplied by R to exponent K. So such a thing is called a geometric sequence. All right? So now, 2, concerning this, I could say that note. Let's compute a limit. So, and let's just consider R to K. So the limit as the limit as K goes to infinity of R to exponent K. Well, let's consider if R is 1, then what's 1 to exponent K? It's just 1, right? So that's like trivial. So if R is 1, there's like nothing happening. So that's kind of boring. What's another R for which this thing is going to end up being trivial? 0, right? Because that would mean that all of these are 0. Now another one that's slightly trivial, but a little bit more complicated is what if R is -1? If R is -1, then it's so famous that it has a name. The alternator, right? So there's sort of like those 3 cases. We've got the case of 1, the case of, which is it's always 1. If R is 0, it's always 0. If R is -1, it's the alternator. Now, what if R is something like half? What will happen to R to K if we keep, what will happen to a number if you keep multiplying it by half? Yeah, it's going to get smaller and smaller and smaller. It's going to go to 0, right? What if we multiply it by -half? So like, what's -half to 0? 1. And then -half to 1 is -half. And then what's -half squared? 1/4. Well, it would be alternating, but it would be shrinking to 0, right? In size. All right. What about if R is 2? So it would be like the first term would be 1, because 2 to 0 is 1, and then the next one would be 2, and then 4, 8, etc. So if R is big, if R is more than 1, this is going to be infinite. What if R is less than -1? If it's less than -1, like if R is, say, -3, it's also going to diverge, because it'd be 1, and then -3, and then +9, and then -27, right? So, we can just summarize all that and say that, well, the limit is 1 when R is 1. Okay. If in absolute value R is small enough, so like half or -half, then it's going to be shrinking. It might be alternating sign back and forth, but it's going to be shrinking. So the answer is going to be 0 when the absolute value of R is less than 1. Right? And then if R is too big, like if it's 2 or 3, then what? It's going to diverge. And if it's too small, like -4, it's going to diverge. And if it's -1, it's the alternator, and that diverges. So it diverges otherwise. All right. So now we want a geometric series. So what about what about the sum from I is, no, I guess k, we'll do k is 0 to infinity of that, a multiplied by r to k. What about that? Which is to say, what we want is, what's the first term in that sequence? It'd be a, and then what's the next one? AR, right? Because you always get the next one by multiplying by r. So that'd be plus, the next one would be AR squared plus AR cubed plus dot dot dot. What about that? So, well, in order for the series to converge, what must be true about the sequence? It has to converge, right? So that can't converge. So that can't converge. When we're not in one of those cases. When r is not 1 and the absolute value of r is less than 1 is false. So it couldn't possibly converge in those conditions. Could it converge in the specific case of r is 1? So what about that specific case? Well, let's take the series and write it. K equals 0 to infinity of a multiplied by 1 to k. Now, what is 1 to k? It's 1. So this would be the sum from k is 0 to infinity of a. So this would be saying add up infinitely many of those a's. Right? And because our requirement for a geometric series is that a has to be not non-zero. Wait. This doesn't have to be positive. That's not true. Rather, it says greater than 0. Rather, it just needs to be not 0. So because this is a number that's not 0, is this going to converge? No, it can't, right? So like you could take whatever number that you like pi. Is pi plus pi plus pi plus pi plus pi plus pi, is that going to converge? No. And if we did it with negative pi, that wouldn't converge either. So therefore, we've ruled out everything except that case. So everything except possibly this. Now we haven't shown that it converges. We've just ruled out every other possibility. So now let's show what happens. So now consider SK. SK, which is to say the kth partial sum. That would be this. It would be A plus AR plus AR squared plus dot dot dot, and then I'll say plus what? I'll say this A R to K minus 2 plus A R to K minus 1 plus A R to K. Okay, so that's SK, right? So now I have a question. What would be what would we get if we did R multiplied by SK? So if we did that. So what I mean to say is if we took all those terms and multiplied them all by R, then what would the first term be? AR, right? So it would be it would be it would be AR and then plus AR squared plus AR cubed. Right. Plus then we'd have A R to K minus 1 plus A R to K plus, what am I saying? Plus AR to K plus 1. Right? That's interesting. So what I want you to observe is that the net effect is that we took, except for the first term, what we did is we shifted all of these over. So shift, shift. There was one there that I didn't write. It shifted. That one shifted into the elision. That one shifted there. That one shifted there. And then there's two new terms. I mean, there's two terms that aren't accounted for in the shiftiness. There's this one and that one, right? Okay. So what if we do the following? What if I say, now please calculate. Please calculate, what do I want to do? I gotta think about it carefully for just a second. I want to do a subtraction, but I gotta make sure I do it in the order that I want. Yeah, I'm gonna do this one minus that one. So now calculate SK minus RSK. So now, because all those terms can be paired up, what I'm saying is that notice that AR is here, and then we're going to subtract away that one. So will there be an AR? There won't be one. What about AR squared? Will there be an AR squared? No. AR cubed will be gone. That one will be gone. That one will be gone. Only that one will remain. In fact, only those two will remain after the subtraction. Because it will look like this. It will look like we have an A, and then we'll have a plus AR, and then a minus AR. And then we'll have a plus AR squared, and then a minus AR squared. Right, I'm just writing them vertically aligned so you can see it. So then dot, dot, dot. Then we'll have plus AR to K, minus AR to K, and then finally, because we're subtracting, what will be the last term? Minus AR to K plus 1. Okay, and then all that stuff cancels there. Then we get this. We get that the formula for SK minus R to like this, minus that, would be A subtract A multiplied by that. Okay. So now, there we've got a nice formula. So now what I want to do is I want to solve for SK. So concerning the left-hand side, do you observe that SK is common? So we can factor it out, right? So if I factor out SK, then what do I need to write in those parentheses? 1 minus R. And so now I can solve for SK, right? So so that means that SK is A minus A multiplied by R to K plus 1 over 1 minus R. And now, this is the kth partial sum. A and R are constant values. They're constants, right? So over here, the only variable is what? Is A and R are constant. What's the only variable? K. K is the only variable. All right, so now I'm going to compute a limit. I say the limit as k goes to infinity of sk is the limit as k goes to infinity of that thing there, a minus a multiplied by r to k plus 1 over 1 minus r. So now a is a constant, so what's its limit? A. 1 is a constant, so what's its limit? 1. R is a constant, so what's its limit? R, right? And then the only question is that this is the only term that's varying, the only factor that's varying at all. And we've already established that the only kinds of r's that we're talking about are r's that are between -1 and 1. So where's that going to go? That goes to 0, right? So that goes to 0. Because r has to be less than 1. So what's the answer? You could write it like this. You could say a minus 0 over 1 minus r. Of course, the minus 0 is a little bit clumsy. So I'll just write this. A over 1 minus r. And therefore, now we have got a very nice formula here. We can say, all right, in fact, the sum from k is 0 to infinity of a multiplied by r to the k. That's a geometric series. So we know everything that there is to know about it. We know everything there is to know. We know exactly when it converges. When does it converge? When the absolute value of r is less than 1. And moreover, we know exactly what it converges to. It converges to that. So this is equal to a over 1 minus r when absolute value of r less than 1, and it diverges otherwise. Ah, very good. So here we have an example. So the first example was, we could do the beer example. So 1 plus half plus a fourth plus a third plus dot dot dot. Okay, that kind of thing. Not a third. What am I saying? 2 to 3. Maybe that's where I got the 3 from, be an eighth. Well, okay, this is a geometric series. So what's the first term in the sequence? 1. So we're saying that so as a result of that, we're saying that a is 1 because a is that thing there. And then what's the ratio? What does it take to shift one position to the right? What's the multiplier? Half, right? So we're saying r is half. So this, if it's anything, has to be the summation from k is 0 to infinity of 1 multiplied by half to k, like that. Right? A r to k. So that's a geometric series. Is it convergent? Yes, because what's the ratio? Half. And what is the condition that causes convergence? Absolute value less than 1. So this converges. And now it's a over 1 minus r. 1 over 1 minus a half. Well, 1 minus a half is half, right? And then 1 over half is what? 2. 2 pitchers, because y'all did this last year. Right? Okay. What if we play a different game? What if we say, okay, what if the first person asks for, say, I don't know, 3 pitchers of beer, and then the next person says, you know what, I'm going to modify that. In fact, we're going to take away some beer. What you're going to have to do is you're going to have to take away, I don't know, like a fourth of the beer that you gave that person. So now you take away some. So we'll say take away 3/4. Take away 3/4, and then we'll say, oh, now come on, more, we don't want to take away beer. We have, we're trying to have a party here. So then what we're going to do is however much that person took away, now we're going to add a fourth of much is however that person took away, which is to say that okay, we're going to add 3/16. And then we're going to take away 3/64, and then we're going to add 3 256ths. That's a hard word to say. Dot dot dot. So this is geometric. So what's the first term? 3. And then what's the ratio that you need to go from this one to the next one? So there to there is -1/4, right? That one to that one is negative a fourth. That one to that one is what? Negative a fourth. That one to that one is negative a fourth. Okay, so the ratio is negative 1/4. So this is a geometric series. So this would be 3 multiplied by negative a fourth to exponent k. So now, that's a geometric series. Is it a convergent one?
Yeah.
Yes. What is the condition for convergence? Right, absolute value of the ratio less than 1. Well, the ratio is negative a fourth. Absolute value of that is a fourth. And that's less than 1. So does it converge? Yes. It converges to a over 1 minus r. So 1 minus negative a fourth, which is to say 3 over 1 plus a fourth. So 1 plus a fourth, that's 5/4, right? And then division by 5/4 is the same as multiplied by 4/5. So this would be what? 12/5. So if you did this crazy thing, then you'd end up with 12/5 of a picture. All right, good. A little more, and then we'll be out of time. All right. So besides geometric series, we now know everything there is to know about it. There's literally nothing else to say. But what I want you to observe is the reason why we knew everything, we could say everything there is to say about it, is because we did this shift trick, right? I said consider the partial sum, and then I multiplied by r, and that caused it to shift by 1, right? And that caused all that neat cancellation. All right. So then suppose that we have the following. Suppose that so I need a remark here. Suppose that we have a sequence an, and an goes to 0, which is to say its limit is 0, so it gets small. I could say define a new sequence Bn. New sequence Bn is going to be an, and then I'm going to say subtract, for example, an, and then down here I'm going to say an plus 8. Now there's nothing special about 8. I'm just writing 8 just to select a particular number. All right. So what I want you to observe is that this is sort of, it's going to end up being like a shift by 8. You know, instead of a shift by 1, I'm shifting it over by 8 units. Okay, and I guess to make my life slightly simpler, since we're running out of time, I will say 4, just so I don't have to write so much. All right. Now let's find SK for B. Let's find that. So what would S0 be? Well, that would be just B0, right? Which would be A0 minus A4, right? A0 minus A4. Okay, then what's S1? S1 would be S0 plus B1, right? S0 plus B1. Well, according to that, that'd be A0 minus A4, because that's S0. And then what's B1? Well, it would be B1, or be A1, I mean. A1, and then subtract which one? A5. So what I want you to see is that and that are that and that. All right. So this would be S2, that would be S1, and then plus B2, right? S1 plus B2. So that would be A0 minus A4 plus A1 minus A5, and then plus what? Right, plus A2 minus A6. Okay. So now, do you observe we keep getting that, right? Pattern like that. So now here's the joke. Suppose that we get down to S4. So I'll skip S3. Well, that would be A0 minus A4 plus A1 minus A5 plus A2 minus A6 plus A3 minus A7 plus A4 minus, which one? A8. So now I need, I'll make it 5 so that you can see the joke. S5. So what's the last one then? A5 minus A9. Now, what's the joke? So notice that for these, there's no cancellation, right? Just for those. Nothing is canceling. And then I take one more bite. Nothing's canceling. I take another bite. Nothing is canceling. I take another bite. Nothing is canceling, right? Because right now all the indices are unique, right? Ah, but do we have a 4? Yeah. Ah, we do. Okay, so I was right. I only needed to go to 4. I don't know what happened. So look, we have subtract 4 and add 4. A4, I mean. We have subtract A5 and add A5. So here's what I want you to see. If we add any more terms after this, there's going to be a cancellation. Right? Stuff's going to cancel away. What will never end up getting canceled? So A0 is never going to cancel. A1 is never going to cancel. A2 is never going to cancel. A3 is never going to cancel. Will A4 cancel? Yes. Ah, it does, right? It does. But A9 is left, right? Nothing's canceling it yet. But notice that this thing that's left over, it's getting small. So here's what I want you to see. So this will be the last thing. So you write out the next few of them. Write out like up to S9. We'll show you what to do. Generally speaking, if SK is big, so if it's like S say 40, then you'll have A0 plus A1 plus A2 plus A3. The A4 will have canceled. Your A4 will have canceled, and then we'll have subtract, you know, some other stuff. Subtract some stuff, and it's all going to get canceled. So here's another way to construct a sum, and this is stuff that's going to go to 0. This sum will converge to those first 4. Ah, okay. So this thing is called a telescoping sum, and we'll continue talking about that on Friday. So have a nice whatever day it is.